Can you calculate this limit? Pause the video and try it yourself. When you come back, we solve it together. As a first approach, we investigate the individual terms x, marked in green, and ln x minus 1 divided by x plus 1, marked in orange. Simply enough, the first term x approaches infinity as x approaches infinity. For big X, the fraction x minus 1 divided by x plus 1 from the orange term becomes indistinguishable from the fraction x divided by x. Hence, the value of ln x minus 1 divided by x plus 1 is equal to the value of ln of x divided by x, if x approaches infinity. Since we know that the limit of x divided by x is 1, the limit of the orange term is equal to ln of 1, which is equal to 0. Therefore, we arrive at an infinity times 0 situation. We cannot conclude the value of the limit from this result. It can also not be concluded that the result is undefined. We need to perform deeper calculations here. A promising approach is to aim to apply L'Hopital's rule. Remember that this rule can always be applied when calculating limits where an infinite divided by infinite, a 0 divided by 0, or a similar situation occurs. In our case, however, we do not yet have a fraction, but a multiplication. Let's rewrite the terms of the limit in question. Remember that this is the limit we want to solve. We can rewrite this using the identity x times a is a divided by x to the minus 1. Applying this to the x in our limit now yields ln of x minus 1 divided by x plus 1 divided by x to the minus 1. Instead of x times ln of x minus 1 divided by x plus 1. Applying the same logic as earlier, we find that we now have a case where both the green and the orange terms approach 0, resulting in a 0 divided by 0 situation. Now L'Hopital's rule can be applied. L'Hopital's rule states that any time we want to calculate a limit of the form f of x divided by g of x, and a 0 divided by 0, infinity divided by infinity, or similar situation arises, we can calculate the limit by calculating the limit of the derivatives of the involved functions f of x and g of x. For our limit, f of x is ln of x minus 1 divided by x plus 1, and g of x is x to the minus 1, or 1 over x. Let's find the derivatives of these functions and see if we can find the value of the limit in question. Let's start with the easier one. The derivative of x to the minus 1 is calculated straightforwardly by the known polynomial derivation rules, resulting in g prime of x being equal to minus x to the minus 2. Let's now tackle the more difficult derivation. In order to calculate f prime of x, since this is a composition of functions, we need to apply the chain rule. Therefore, the derivation of ln of x minus 1 divided by x plus 1 is equal to the inner derivation obtained by focusing on the green term, multiplied by an outer derivation obtained by focusing on the orange function. Let's first find the inner derivation. The inner derivation is obtained by differentiating the fraction x minus 1 divided by x plus 1. Here, we need to apply the rule for differentiating fractions, where the derivative of the fraction u divided by v is equal to u prime v minus u v prime divided by v squared. This results in the derivative of x minus 1 divided by x plus 1 equaling 1 times x plus 1 minus 1 times x minus 1 divided by x plus 1 squared. Note here the matching color coding. This can be further simplified by not writing the redundant multiplications by 1, resulting in x plus 1 minus x minus 1 divided by x plus 1 squared. Further simplifying the numerator by resolving the brackets leaves us with x plus 1 minus x plus 1 divided by x plus 1 squared. Note here the rule for resolving brackets with a negative sign in front, equaling 2 divided by x plus 1 squared. With this, the inner derivation is found and simplified as far as possible. Please remember to leave a like and a subscription if you want to see more content like this. With the inner derivation found, we now calculate the outer part. For this, remember the rule for differentiating logarithms. The derivative of ln of u with respect to u is 1 divided by u. Therefore, the outer differentiation is simply the inverse of the term inside the logarithm. Remembering that inverting a fraction is equal to exchanging the numerator and denominator, we arrive at the outer differential being equal to x plus 1 divided by x minus 1. With this, we have calculated the derivative of our function f of x. However, we may be able to further simplify this expression. Noticing that the term x plus 1 occurs in both the denominator and the numerator, we can cancel these terms, resulting in f prime of x is 2 divided by x plus 1 times x minus 1. Resolving the binomic formula in the denominator, we arrive at f prime of x is 2 divided by x squared minus 1. Remember that we started with the functions f of x is ln of x minus 1 divided by x plus 1, and g of x is x to the minus 1. We now have found the derivatives of these two functions, which enables us to apply L'Hopital's rule to the limit we want to solve. According to L'Hopital's rule, our initial limit is equal to the limit of 2 by x squared minus 1 by minus x to the minus 2 as x approaches infinity. This double fraction can be rewritten as the limit as x approaches infinity of minus 2x squared divided by x squared minus 1. Since this again results in an infinity divided by infinity situation, we can again apply L'Hopital's rule. This time, the derivatives of the functions in the numerator and the denominator are simple polynomials, resulting in the limit of minus 4x divided by 2x as x approaches infinity, where the x cancels out and leaves us with the solution of minus 2. Therefore, the value of the limit from the beginning is minus 2. This one was quite complex, and we can think of at least 2 other methods of solving this one. Did you come up with a different approach? Then please share your solution or idea in the comments. Thank you very much for watching. Please leave a like, a comment or a subscription if you want to see more content like this. Until next time, and see you soon!